All right, welcome back from the break, and thanks to Doug for that great talk about the Sea Bridge. We're going to shift gears a little bit now and instead talk about something more on the portable radio side of the system, and that is how we can use DMR radios to transmit IP data traffic, sort of in addition to the voice that we're normally used to. And so this presentation is going to focus mostly on Motorola radios since they implement the features that we're going to be demonstrating here. Believe this might also be possible on Kenwood models as well, but most of the Chinese radios, at least the ones that I'm aware of, do not support this functionality. But I do think this is interesting for everybody because we do have a lot of cache radios that we could leverage for doing things with this later on. And I think it opens up a lot of doors beyond what we normally use the network for. So let's talk about DMR beyond voice. If we sort of take a networks approach to DMR, we can sort of build up a protocol stack the same way that we would for TCP/IP, Ethernet, Wi-Fi. And it starts down at the physical layer. This is the air interface, the channel coding, the concept of time slots. This is stuff you mostly don't have to worry about. It's sort of handled for you by the radio itself. And on top of that, we build the network layer. This is where you start becoming familiar because we're going to start adding things like the talk group IDs, radio IDs, the identifiers that basically build the DMR network on top of the RF interface. And then we're going to throw on the voice. And this is where most people kind of stop, right? They use DMR for phone, voice communications. Maybe they use some of the other features that are lumped in with what the standard calls control signal blocks. And this is stuff like the man down feature, call alerts, a lot of these things that maybe are buried in your menu on a DMR CPS that you don't really use too much for ham, but have kind of maybe played with before. And then we're going to expand and slap on this entire data portion of the stack, right? So this is where your text messaging comes in, location tracking. If you're on a Motorola commercial system, you might be familiar with something called ARS. That's for basically automatic presence and mobility detection of radios as they move around the network. But if you are looking at that extra spot there in the corner, you are ahead of me because that is where your data can go. Just as much as DMR supports voice traffic, it supports end-to-end IP data originating from the mobile stations, that's the radio that you're carrying, transiting through the network, and from there going on to either network services or another radio on the other end. And that's what we're going to talk about mostly today. And to build off of this, the DMR designers basically recycle a lot of network concepts that we are very familiar with as network engineers and computer programmers. So the data layer right here is very analogous to UDP. It actually has a concept of port numbers, and as we're going to talk about later, you can actually map DMR group and unit IDs into IP addresses. So if you've ever done a deep dive into the Moto Turbo CPS, you may have noticed a lot of clues about the things that I just mentioned, right? We take a look at the sort of services menu. All of a sudden you're seeing things that look kind of like you're configuring a server application on a computer, right? You got UDP ports, IPs, server ID. In the channel settings, there's something called a compressed UDP header, all these ARS settings. That's like pretty interesting. And if you're ever bored on an airplane without Wi-Fi or something, just open up CPS and just check on expert mode, and just read everything that's in there, because you're going to discover all sorts of cool features in there that you probably haven't played with before. So logically, it follows that your radio is actually some kind of intelligent network device. And believe it or not, your radio is actually a network card / modem. So when you plug your Motorola radio into your computer, that is actually enumerating as a USB Ethernet card. And the radio hosts a DHCP server that provides to you an IP address. And when you are programming the radio on CPS, it's actually opening a TCP connection to that radio, and that's how it uploads a code plug to it. The default is 192.168.10.2 assigned to your computer, and the radio takes .1 in the same subnet. Most people only use this for programming, but as we're going to see later, this becomes your gateway to the DMR IP network. Because as it turns out, your radio is actually a router as well. Nowhere near as fancy as the MikroTik routers that we use in our core network that Doug was talking about. But it has multiple IP interfaces, and it has a way to move traffic between them. That, in my book, is a router. And let's go ahead and take a look at some of those. So we've already talked about the USB connection. That's how we mostly program. There's also a Wi-Fi interface that I believe is only used for radio management type applications. There's also Bluetooth personal area network. And of course, the radio has all sorts of internal services, for code plug upload and text messaging. We'll talk more about the text messaging later. And then on the other side, we have the DMR Common Air Interface. If you haven't heard that term before, the CIA is basically just the term that refers to the standard DMR RF interface, for lack of a better word. This is what is coming off the antenna of your radio. And you can see that there are basically two IP ranges present there. And we're going to talk about what those mean next. So I mentioned earlier that you can map your radio IDs into IP addresses. So the way that that works is we take the 24-bit individual ID of the radio, and we're going to basically remap those 24 bits into 3 of the octets of an IP address. The easiest way that I could think of for people to work this through is basically convert your ID to a hexadecimal. You should get 6 hex characters right there, 24 bits. And then convert each of those individually back into decimal, and that's how you can do the mapping. The 12 is sort of an arbitrary number that gets set in the CPS. 12 is the default. I don't know why that is the case, because that is actually a public IP address that I think belongs to AT&T. They could have done 10 and gotten just as much space. I don't know. You can change it, but might as well just stick to 12 because this shouldn't actually touch the real world anyways. For groups, I'll get to that in a second. For groups, we use IP multicast space. So it's the exact same process where a 24-bit group is mapped into, I believe it's Class D network space. 225 is the default prefix there again. I don't know off the top of my head what prefix that is actually under, if it's in the sort of free use multicast space. Do you know? No. Well, anyways, it shouldn't matter if you're setting your stuff up correctly. But yeah, basically your radio will be subscribed to that multicast group, and stuff you send to that address gets multicasted throughout the talk group. So the 13 dot. The DMR specification says that if you take the CEI network number, which is 12 in our example, and you add 1 to it, that becomes the IP address of the, quote, accessory attached to the radio. So in our case, that's going to be a laptop connected via USB to the radio. That laptop basically assumes the IP address of 13 dot whatever. And then 12 refers to the radio specifically. So let's go ahead and pretend that we're attaching a laptop to our radio. Like we said earlier, the radio is a router, and we need to teach our computer how to route data over to that radio so that it can transit the network. Remember, we're only 192.168 dot something so far, so we have to basically insert our own entries into the routing table. Basically, just tell your computer 12/8, 13/8, send it to the radio. The radio knows what to do with that. It will basically forward those packets through the Common Air interface out to the DMR network. But this is really important, otherwise your computer is going to have no idea what to do with a 12.IP address. Probably it's going to route it out your default gateway out to the internet, and then some AT&T customers are going to be getting it. I have found that you can use smaller subnets if you have your IDs sort of lumped into a smaller range, but don't see a great advantage to doing that unless your DMR network is ginormous. All right, so this is going to bring us to the first of a couple of pre-recorded demos that I have prepared. So what we're going to see in this example is, on one side we have the mobile station, which is a laptop connected to an XPR 7550E over USB. And then on the other side, another UHF DMR radio. This time it's a mobile unit, also attached via USB to this laptop. And I want to stress, there is no connection between these two. It's purely wireless. These are not networked in any way, so this is a real-world example. I am using simplex operation in this case, but it's no different to this. We're going through a repeater, and it would also transparently go through a C bridge. So for demo one, what's the very first thing you do when you plug something into the network and you want to test it? Ping, of course. Exactly. Fortunately, none of that happened, or if it did, I would have done a second take. Let's take a look at what's going on in our ping command, because it's a little bit longer than usual. So we're using a 12/8 address, right? .100, because the radio on the other end has an ID of 100. I'd use small numbers just so we didn't have to deal with using multiple octets. But that is the IP address of that other radio. That one, to be exact. The P, if you're familiar with ping, is a pattern flag. And that hexadecimal jumble right there is my call sign encoded as ASCII as hexadecimal. And the reason why I'm doing that is because of what Doug mentioned earlier in his previous talk. DMR is not intended for amateur use, and it will not identify properly for you. It is on us to make sure that we embed our call signs into the communication through some easily readable means. I think ASCII is perfectly acceptable. And if you were looking at this going over the air in Wireshark, you would very clearly see NM0TH repeating in the ping packet multiple times. And if you experiment with this stuff, you should find some way to make sure that your call sign is represented, whether that's manually sending ping packets every 10 minutes or incorporating it into whatever protocol we build on top of this. The I is a timeout. We are allowing 5 seconds between ping packets here. And that's going to be one of the major limitations that you see later on when we're using this. It takes a long time to set up a data call to get that packet through. It's a little bit better as you're sending subsequent packets, but for sending out little pings like this, we do need some more time in between. And just to help things out, I'm making the packet a little bit shorter, only 24 bytes. All right, so now that we know what we're going to be sending, we can go ahead and take a look at the demo. And I'm going to try to drag this over to the correct screen. I might have to interrupt the presentation temporarily. All right, so we're back in my lab. Here's the radio that we are sending the pings from. And we are slowly but surely getting responses back from the radio on the other end. Here we got Wireshark open. We'll come back and take a look at this in more detail. And like I mentioned, you can see the call sign right here at the end of the packet. You can see the activity light is blinking on that radio. No sound's coming through, but it's doing stuff. We are basically pinging the internal IP stack of that radio. Yes?
I know from networking and from radios, and when networking is full duplex. Radio is not.
Nope.
So how is it actually just? It's when the packet goes out, it transmits one way. When the packet has to come back, it transmits the other way.
Yeah, it's switching back and forth, and that's one of the reasons why we have to be pretty careful with what we're sending. It is very easy to overwhelm this interface, and before anybody asks, yes, I did try putting TCP connections through it to see if I could, load a web page over radio. That did not work out at all. Maybe if you could really carefully tune your TCP stack parameters and shrink the window size down to just one and wait. Yeah, maybe you could do it. But yeah, that's not the kind of traffic that you'd be targeting with this. And I'll go on some proposed examples and possible use cases at the end. But yeah, the radio does have to internally switch between transmit and receive in order to make this work. Yeah, so interactive stuff is hard to do, and ping is honestly pushing it. But we'll do some more demos. The next one is going to be an interactive chat with Netcat.
Well, we're essentially facing the same problems as the people in the Deep Space Network does.
Yes.
The latency is out of this world.
Absolutely. Maybe we can someday use DMR on the Deep Space Network to talk to astronauts. All right, let's go ahead and return to the presentation. So we talked about Wireshark. Let's go ahead and take a look at everything that's going on here. So yeah, we mentioned that the long ping times are happening just because its radio access is slow. It also has to do, carrier sense and everything right here, because there could be somebody else using the RF channel at the same time. So it has to be sure that it's not going to clobber somebody else, and you can probably fine tune how polite it is. This is Wireshark displaying the USB interface, or sorry, the packets going over the USB interface. .10.2 is our laptop, remember? And then .100 is the radio on the far end. So you can see that there's some network address translation happening. It's masquerading the packets for you. And like I mentioned earlier, we have legal identification included in the packets right here. You can see my call sign sort of embedded in the last couple of bytes of the ping packet. Yeah, so demo number 2 that I just alluded to. This is basically, we're going to use Netcat, which, if you're not familiar, is a very popular Linux, Unix utility for terminating network connections, and you can either type into it or pipe other processes through it. Sort of the Swiss Army knife of UDP and TCP network troubleshooting and testing. One thing we have to do, sorry, my mistake. That's going to be demo number 3. Demo number 2 is DMR text messages. Sorry about that. So DMR supports texting, and you may have played with that before. Motorola has their own sort of proprietary text message format that is different or extended upon the standard DMR one. So if you want to play with this, go into your code plug and change text message type to DMR standard in your channel settings. And you're also going to want to go ahead and enable forwarding to PC. This basically instructs the radio that any text message package that come in just passes along the USB interface, and then it ends up at your computer, I believe sent to port 5016. But I'll have that in the slides shortly. So what's going to happen in this demo is one of the PCs is basically going to send a text message originating from the computer to the portable radio on the other side. And then we're going to wait for a reply to come back. So yes, it is UDP port 5016. Your radio is basically running a UDP listener server on it, on that port, and stuff that comes in there gets displayed on screen as a text message. You do have to make sure that you encode your characters as UTF-16, big endian, but that's not hard to do. So let's go ahead and swap over to the video for this demo. All right, so this is a little Python script that I wrote that just basically handles the unit ID conversion to an IP address and also doing the text encoding. It's not plain ASCII. They support a broader character set. The UTF-16 big endian is specifically what they use. So in my little script right here, 101 is the destination unit ID. Here's my message, and I'm including the -reply option because I'm just going to wait for it to receive a packet back. All right, so let's go ahead and watch what happens. So it showed up there on the radio. I'm going to reply with a canned message, send that, and then there we go. Okay, so that was a little bit fast. So let's go and head back to the slides and basically deconstruct everything that happened there. Okay, so like we mentioned, port 5016 is what's used for standard DMR texting. So originating from the laptop and going to the radio, 12.00.101, we have the actual text message packet, and that's what I have highlighted down here. So you can see, again, the text is encoded right there, UTF-16. And on top of that, we have the standard UDP header. That's all it is. There's really nothing else you have to include here. And then the reply is basically the same thing, but it's just coming in the opposite direction, right? So it's originating from 12.00.101, coming back to my computer. And yes, now the demo that I mentioned previously, this is the netcat chat. So because we're going between two computers in this case, we're using the 13 dot addresses this time. So that's 13.100 for the control station radio, and then for the laptop attached to the control station radio, and then 101 for the laptop that is attached to the portable unit in my setup. So we're using 9000 as an arbitrary port. Netcat is set up as a listener on one of the machines, and on the other side, we just have a netcat client running. That's how you would invoke it. And we'll switch over to the video once again. All right, so we got netcat running. I have a message typed. Hit return to send that. And there it pops up on the other end. Go ahead and type a response. And there it comes through. The latency actually wasn't that bad on that one. And we'll get another close look at the Wireshark transcript after the video. But there's really not much to it. You can send UDP packets, you can make them go over your radio, and they just come through. Yeah, and I think you get the idea from that. like I mentioned before, using the 13.IP addresses, that's 12 plus 1, because we're talking to the accessories attached to each radio. And there's just a bunch of UDP ports, or sorry, UDP traffic going back and forth. So just to cover a little bit more of the DMR data terminology that you might see in the specification if you dive into this more. Confirmed data, this is a setting you might have seen in your channel settings before. Most people don't know what that means. But when you have confirmed data going over DMR, that basically means that the radio on the other side is going to acknowledge that packet for you. And that's obviously desirable, but it presents a problem for Part 97 operation because you're basically causing somebody else's radio to make a transmission, and they may not know that's happening, and it certainly isn't going to ID for them properly. So for amateur use, you should probably not be using confirmed data unless you can be absolutely certain that whoever's on the other end can take care of the identification requirements for their radio. Unconfirmed data, which is what we do use, does not have a retry mechanism built into the standard. That's something you would have to add by yourself. It does have a checksum to make sure that the packet didn't get malformed in transit, but it will get just silently dropped on the radio if you're doing unconfirmed data and there's a transmission error. You can use different channel coding options for your data traffic. You can use what they call rate 1 data, which basically means that there's no forward error correction or channel coding applied to your traffic. It's the highest bandwidth, but obviously the most risk of something going wrong in transit. There's still a checksum, but it's going to have a very hard time recovering from any bit errors. There's rate 3/4, 3/4, where they use a trellis arrangement to add some forward error correction, but still give you a decent amount of capacity. The 3/4 basically means that 3/4 of the packet carries your user data as opposed to checksum information. And you can also do half rate data, and that uses what they call a block code turbo checksum. I can't remember what the acronym actually stands for. It's another forward error correction algorithm defined in the spec. It has nothing to do with Moto Turbo, even though it uses the same word. And that gives you basically half of the space in the packet for your data, and then half is checksum information. So that's the most robust form. Which one actually gets used? I think you're gonna have to take a look outside or inside your CPS settings. Then obviously with unconfirmed data, that's something that you can multicast to the entire talk group because you're not expecting any of those radios to actually reply to you. We have covered identification, but just a reminder, as we've preached in the previous talk, your DMR ID is not good enough as far as the FCC is concerned. The IP address that your radio magically maps to is not good enough either. There's no ARIN for DMR IDs that's going to be managing your IP allocations. So once again, you have to handle this on your own, whether that's making sure that you're sending your own packets with your own call sign every once in a while, or if you are developing some kind of application layer on top of this that you are including provisions for a call sign to be attached, especially if you're doing this in some kind of automatic, like telemetry type operation. Encapsulating AX25, that could potentially be an option. That would take care of the identification requirements, and then maybe you could tunnel APRS data over DMR, which is kind of crazy. But on that topic, we can go ahead and talk about some of the applications that I'm sort of envisioning for this. Because it's actually really easy to use. As long as you can stuff the routes into your computer or whatever you're attaching, and you can do basic network programming, which I did with like a 10-line Python script, you can sort of unlock a whole new powerful world of DMR traffic applications. And the first thing I want to address is, well, why do we need any of this when we already have a perfectly good data packet mode in amateur radio, i.e. APRS? And I'm not saying this should be the replacement in all cases for APRS, but there's some cases where this might make more sense, and that is if you want to leverage an existing DMR network, right? So like this club often does public service events, and a lot of times these are in remote areas where we have to basically bring our own infrastructure. Does it make sense for us to bring, 10 DMR repeaters, but then also, 5 iGates and analog radios for each station and TNCs when we already have a DMR infrastructure? Probably not. And maybe this is a good place to use something like that. The data is also more robust. APRS and specifically X25 do have checksums, but they don't have forward error correction. So if your packet encounters any kind of bit corruption in transit, the packet is ruined, and you basically have to throw it away. DMR, depending on what channel rate you're using, has some allowance for bit errors before the packet becomes unusable. It can actually do correction on those bits. So one thing I really want to see this get used for, and I know that some of the EOS guys are pretty interested in this as well, is basically start developing database applications for deployments, whether that's public service or some emergency scene. Because when you think about it, a lot of the traffic that we have to communicate when we're doing something like a race or a marathon is pretty routine and honestly tedious to have to speak out, right? A lot of times it's reading bib numbers to make sure that we can account for runners, or monologuing a resupply request where you're just listing out part numbers or supplies that your station needs or check-ins. A lot of that stuff isn't great to do with voice. And if we could develop a simple computer application where we have a DMR radio on a laptop at each water or medical station that somebody can basically just type into, say like, yes, status is good, or we are out of bandages. That takes a huge load off the network, and then we can use voice to focus for the non-routine stuff. Like when something atypical happens, you can jump right on. You don't have to worry about some long-winded conversation taking up the network. And while it does still take a couple seconds for these things to go back and forth, that's way faster than it would take for you to communicate this information by voice. And you could also punt this off to a different time slot. The other thing that I think could be a lot of fun to play with are basically creating gateways, maybe for text messaging. You can basically leave a radio on your desk hooked up to some computer application that could, forward your messages over SMS or something like that. I don't know what the legalities of linking that sort of stuff is, but a lot of opportunity there to play around with that stuff. Or maybe you can do the other way, and you can have your weather station hook into your DMR radio and then broadcast weather information for other hams to consume. A lot of cool stuff that you can do with this. If you do want to learn more about this, the ETSI DMR specification, which is a pretty advanced document, but it does go into extreme depth over how a lot of this works. It looks like Paul actually has a printed out copy of it on his table over there. I hope you bring that up for your talk. Excellent. Yeah, this is an extended length session that's actually going to go until 4 p.m. tomorrow. He's going to read every paragraph from that. Another piece of not so much fun reading is the CPS help pages. Like I mentioned earlier, there's a lot of functionality documented in CPS that most people don't ever touch. Go play around with that. There's a lot that you can learn that you may have never even known your radio supports. All right, so that's the end of my slides. Do you have any questions? I also want to talk a little bit about the steerage side of things, since that's been sort of a new development since the last time I presented this.
So what is the effective data throughput, if you were to think of it in terms of bits per second, that you get with DMR?
Yeah, John just said bits per minute. It's a little bit better than that, but it's not great. So a fully encoded DMR stream across both time slots is 9,600 bits per second. divide that by 2 for one time slot, 4800. From there on, it depends on what your channel encoding rate is. I mentioned the 1/2, 3/4 earlier. That influences how much traffic you're going to be getting through. If you're using the most robust half rate, divide that by 2, 2400 roughly. And then, of course, there's going to be a call setup and teardown time at the start and end of that. For the most part, you're probably going to be sending short messages and paying that price to set up the call each time. But if you were doing a more extended exchange, streaming a file or something, for example, then you would gravitate more towards that 2400 or whatever channel rate you're using.
So if I did the math correctly, in effect, if we have 4800 baud, we have 20 millisecond packets. That's basically 96 bits per time slice, which is essentially 12 bytes, right? So if you're going half rate, you're essentially sending 6 bytes every time slice that you get, right? So keep that in mind. Don't be sending photos.
Yeah, that's an excellent point. And if you go into the specification document, they will actually show you a byte-by-byte breakdown of what goes into the packet, depending on what settings you're using, confirmed, unconfirmed, channel rate, and also all the which fraction of that is encoding bits and stuff like that. So definitely we recommend reading that, but it is an excellent point. If you can squeeze your message to fit into the boundary of one packet size, whatever that may be in your application, that's going to make a dramatic improvement on your throughput because you don't have to start fragmenting your stuff. And another thing to consider is that there is actually a UDP header included as part of this data, so there is overhead on top of the traffic that you're trying to get through. There is a way to compress that UDP header because it's actually quite large for an RF application, and that does save you a couple of bytes. But you do have to consider all that. Did you have a question? Yeah.
Okay. My question, when you were at the beginning setting up the computer,
Yeah.
when you were adding the,
You want me to go back?
well, that's okay, the 12 and the 13
The
IP,
routes?
yeah, the route. Can you have that pre-set up in a host file so you wouldn't have to do that every time?
You could certainly automate that, depending on whatever. Sorry, one slide back.
Yeah, right
Yeah,
there. Yeah.
absolutely. Whatever network manager your system uses could probably have these routes pre-configured. Network manager certainly can.
Okay. I was just thinking about that when you were putting that through, so you wouldn't have to do that every time.
Yeah, I do want to caution you, though, that you don't want to leave these up full time, or at least you want them to go away when that interface is not present, because this will absolutely interfere with a lot of cloud-based services. 13 has a lot of cloud data centers using that range, and you probably don't want your email and websites to randomly not work because you have a broken routing table. But that should not be too big of an issue either.
There's also an interesting comment when you've got this set up. If you've ever programmed a Motorola radio and you have your programming cable plugged in, it will rewrite your default gateway and send all the traffic out to your radio, and then all of a sudden your computer can't route. So you have to unplug the programming cable to get it to figure out how to get to the world.
Interesting. I don't think I've had the problem where the default gateway changes over to the radio on my
I have
system.
many times.
That's unfortunate. Yeah.
It's Windows.
It's Windows. Any other questions? Anybody have an idea of anything that they want to do with DMR data traffic? Carl does. What are you thinking?
I want to see EOSS do something with it, and I happen to know that N2XGL is on this Zoom call, so.
Yeah, so I actually spoke to them the last time we talked about this, which I think was spring of this year, and they were very interested. And I think their application would be something along the lines of distributing tracking updates and chase car coordinates to their other members in the caravan. So if you're not familiar with what the EOSS does, is they're a balloon launch, edge-based sciences organization. So they basically run these educational balloon flights every couple of weeks. They do a lot. And they use our DMR network a lot to coordinate their tracking and recovery efforts. So they all jump in their cars and basically chase these balloons through eastern Colorado. And to keep in sync with their group, I think one thing they're considering doing is...
There's a question from the chat here.
Yeah. Is it about EOSS?
No. Perry Lundquist says, hold on, there it just jumped on me. Couldn't an open source chat application be configured or adapted to use do DMR, data over DMR for short messaging? And then Nate says a good Python programmer could probably fork DRATs from low-speed D-Star world to make a Moto IP compatible version fairly quickly.
Yeah,
IRC.
I don't see why any of those wouldn't be possible.
In your copious amounts of spare time, why don't you do that?
Yeah, I do not have copious amounts of spare time. He's lying.
I heard him volunteer, didn't you?
So are we up on red? So as Tristan was speaking about the possible uses, one of the things that we have available to us is you're probably saying, well, I don't have a Motorola radio, or I've got a Chinese radio, but we do have a reasonable stock of Motorola cache radios, and we've recently, Rocky Mountain Ham was donated about 40 VHF DMR mobiles that we are going to probably make available to our partner clubs, ARES, regions, districts, other resources that we can send some of this DMR data, and that's one of the reasons Tristan's going down this road. I really like the idea if we somehow can encapsulate an AX25 stream into this, or a WinLink stream that can be identified in that one of those formats. But if we can't, we're going to find a way to do this, and DMR data might be useful to you, especially when you consider an AX25 on 145.01 today. You've got a 1200 baud, it's half duplex, so cut your channel time in half there, because you're transmitting, receiving, and back and forth. But once you get into one of our DMR repeaters, we're now sending this through the backbone, and we can go long distances. There's not that store and forward anymore, where the throughput rates are continually dividing by 2. So
Meeting N2X.
I really appreciate what Tristan's looking into, and appreciate this talk.
Yeah, and I'm glad you brought up that donation again, because I think our vision for those is basically create a couple of data-ready, deployable radio kits that we can distribute to partner clubs and people that are interested. And so having DMR data IP support on there is an option, maybe even having a TNC for traditional APRS as well. We would pre-program these things to have some common channels and some common channels set up, and maybe even a laptop attached with some pre-installed software to use all this. One thing that does remind me about, though, is if you are experimenting with this stuff, we have a rule at Rmham that we don't allow data services on most of our talk groups, but we have specifically allowed it on the Eastern. I believe that's 719. No, that's 705. 705 is Eastern. That's mostly present on VHF repeaters, and you can have at it there. You can send as many obnoxious GPS status updates and text messages as you want, and that won't disrupt other people.
So
Yeah.
there's a question here
identify.
from Eric, KE5 Z Bravo Golf down in New Mexico. Is there an issue with switching to UDP compressed header for some transmissions and then back to uncompressed?
I believe the radios will understand both. It's part of the DMR standard. Probably you want to be using it no matter what. It gives you a lot more space in the packets.
So if you've done, with some of your plan with the VHF, have you been successful running this through a repeater? Or are there some challenges in, in the future if we want to, talk to everything on that site connect or going through a bridge? I know it's not supported with what we have now, but have you done any of the testing on that?
Yeah, I have experimented with the C bridge to figure out how its data groups work. And I believe I have successfully set it up among some of the East group repeaters. It's really buried in the C bridge configuration. It's not part of the normal bridge groups. I can show you guys what it looks like. I did want to actually try to pull some screenshots from the C bridge in here, but I was having trouble accessing it over the network in here. But maybe we can try looking after the fact. All right, unless there's any further questions, thank you guys so much. And thanks for all the great questions in the room and on the phone. Hope you guys play around with this and do something cool with it.
All right, next up is Paul Olson, K0WSU, with vocoders and other magic.